All right, let's get going. So this is Professor Vijayaraghavan's second lecture.
Third
lecture already. Oh my God, time flies. Okay, I hope you'll give a fourth and a fifth as well. Anyhow, this is third lecture, and we're going to hear about superconducting electrical circuits.
Hey, good morning and welcome back. As I was looking at my slides just before coming here, maybe I'm a little too ambitious that I'm going to be able to cover all these things, but let's see how far we get through. Just as a quick recap. Yesterday, we discussed the basics of the qubit measurement setup, what goes in both at room temperature and cryogenics. I explained to you the sequence of steps one typically has to go through to characterize the qubits. So like doing spectroscopy to find the transitions, and then coherence measurements to do your relaxation and dephasing times. And then we discussed a few different types of superconducting qubits, starting with the so-called charge qubit or the Cooper pair box, which was sensitive to offset charges affecting the charge on this island and resulting in frequency fluctuations, which are bad from the point of view of dephasing, to a slightly improved design called the contronium, where we went to a specific bias point in this gate charge where you become first order insensitive to charge noise. And that improved the coherence significantly. This was more than 20 years ago. And then finally to the transmon, which the parameters of which are chosen in such a way that now the Hamiltonian becomes extremely insensitive to charge noise. You pay a price in terms of the nonlinearity of the multi-level structure, but that price is not that high. The charge dispersion, which is basically the difference in the transition frequencies for having two charges differing by one electron, is suppressed exponentially, whereas the enharmonicity doesn't get suppressed so much. So you can make a good qubit, and 2007, which was first demonstrated, and it's the most successful qubit design till now in terms of practical application. All your large-scale quantum processors available today are made using this simple Josephson junction nonlinear inductor shunted with a capacitor, which is insensitive to charge noise. So today I will discuss one more type of qubits and some of its variants, which is also very interesting both from the physics point of view, and it's slowly emerging as a possible candidate to replace the transmon. It's still sort of not as advanced in terms of demonstrations of quantum gates and things like that, but it's sort of getting there. And this idea is again looking at an alternate way of suppressing the charge noise problem, but maybe without sacrificing the enharmonicity. And this device is called the fluxonium. And this first paper came out in 2009 from the group of Michel Devereux at Yale. And the title of this paper is Single Cooper Pair Circuit Free of Charge Offsets, the fluxonium. From the circuit diagram, if you just pay attention to this part here, it's a trivial modification. So you have your Josephson junction like before, and you have your capacitor shunting it. But now you have a linear inductor shunting it as well. Okay? The parameters of the Josephson inductance and capacitance are different. They are actually closer to what the charge qubit parameters used to be. But by adding this linear inductor across it, it sort of shorts out the offset charge effects. Basically, this inductor, with this sort of a hand-waving way of understanding, is that doesn't allow charge difference to appear between these two, or doesn't allow the island here to accumulate any offset charge. And this inductor essentially sort of shorts it out. And typically, because these offset charges cause low frequency noise, you need an inductor which can short it, but this inductor has to be big enough that it sort of doesn't affect the Josephson inductance so much. Otherwise, this system will become linear oscillator, right? If this inductance was very small and it's in parallel with an inductance which is larger, then effectively the total inductance is the small one, and that's the linear part. So you need to balance these out, and that's sort of balancing act of choosing the right value of Cj, Lj, and La or equivalently in terms of energies, charging energy, Josephson energy, and inductive energy, you get into this parameter space called the fluxonium. And this inductor turns out to be something that is non-trivial to make, because the value of this inductance you need is big enough that it turns out that it's actually not possible to build such an inductor by just having a piece of wire. Like, how do we build inductors in our electronics labs? It's some loop of wire. In superconducting circuits is some thin film which is sort of wrapped around on the chip. But because of the parameters of relative permittivity and permeability, or in some sense the fine structure constant as well, turns out that you cannot build a geometric inductor which is large beyond a certain value. And it's got to do with the fact that any physical structure which is big is also going to have capacitances associated with it. And it's impossible to suppress that if you just try to build it with like a piece of wire. So the solution is you need to find some other mechanism, and we already know that because Josephson junction provides an inductance. But you need, if you make this junction if you need a large inductance, you need a junction with a very small area. So that's not a great idea here, because then it'll sort of start affecting the properties of your qubit. So instead, what you do is you make an array of Josephson junctions. So this circuit here is showing you that this part, the small junction and the capacitance is here. And this linear inductance is replaced by an array of Josephson junctions, which are somewhat larger in size. So they are big junctions compared to this one, which means their inductance is smaller of each of the junction. But you put them in series and you maybe make something like 50 or 100 or so, and you get a large enough inductance. And this kind of an inductor, they gave this name of a superinductance, because you can get inductance with impedance much larger than the resistance quantum, and that's sort of the crossover point which is difficult to break. And then if you do that, it also ensures that it sort of remains linear, because the critical current of these junctions being larger physically larger is also large. And the characteristic currents that are going to flow in the circuit are actually set by the critical current scale of the small junction. So the excitations here are not going to be very large in current, and you don't access the non-linearity of the array that much. Okay, so it's a good approximation for building a linear inductor. Just as an aside, in the last few years, people have figured out other ways of making this inductor, which looks like a geometric inductor, like it's actually a wire, but it's actually made of highly disordered like superconductors. And the model is that it effectively creates an array of Josephson junctions. But the fabrication technique is slightly different, and it has some advantages, something called granular aluminum-based inductors. This one here? This one? What is the downside? Oh, yes. So you have to engineer this very carefully. For example, this gives you a slightly more explicit circuit model that, so there is a Josephson junction. It has its own capacitance shunting it. And then there are these sort of stray capacitance which are connected to ground. This physically comes from having an extended chakra, and that there's some ground plane reference somewhere. And if this capacitance becomes too high, then it no longer behaves like a simple linear inductor. The second thing is that you have to be careful that you don't have phase slips happening in this array of Josephson junctions. Essentially, a phase slip is like if one of these junctions sort of undergoes a full pendulum turn and creates a twist in the phase, as opposed to having the phase linearly distributed across the junction. When you have a total phase of phi, then the phase drop across each individual junction is just phi over n. So that's what you expect for a linear inductor. But if you don't have the parameters of these junctions and the capacitance just right, then you can have these phase slips, and that can add to a coherence process. So the way they design this is that that phase slip can only happen at the small junction. And in fact, that's sort of the main feature of this thing. So before this experiments with arrays of Josephson junction have been done, but sort of never in this regime. And this was the first time they made this clue. And as you'll see in a few slides from now, they have made even more crazier junctions, arrays of this, by doing some very clever tricks to minimize this capacitance. And that's really sort of what sets the limit of how high an impedance you can make. And that determines the kind of parameter regimes you can implement in your Hamiltonian. Okay. Now, if we think about what the potential of this kind of a circuit is going to look like, you can just combine what the potential of a linear inductor is and what the potential of a Josephson junction is. So Josephson junction is a periodic cosine potential, and the linear inductor is a parabolic potential. So if you sort of have the parameters in such a way that they kind of overlay on each other, then you end up getting something like this. Okay. The top graph here is the potential profile when this phi external, which is now the flux you can now apply in this superconducting loop. There is now a loop introduced in this problem. And you see the Josephson modulation on top of an overall parabolic potential over there, right? So it's not very clear because I've only done a few undulations here. But if you now apply a small flux offset, which sets up a circulating current in this loop, it sort of biases your Josephson junction at a finite current, and that gives rise to a little bit of a tilt. So if you look at these two here, so here this right side potential is slightly tilted and this one is lifted. So you can sort of distort this potential. And in just a bit, you will see the operating point where it's used as a qubit, what the potential looks like. And it's something I had mentioned, I think, in my first talk as something that would be the ideal type of qubit profile. Okay. So again, I want to reiterate that by combining these circuit elements in different ways, you really have a lot of flexibility in sort of constructing a designer Hamiltonian, depending on what you want and how you want to protect your circuit from the environment and so on and so forth. Okay. So at this point, I'm going to again shift to the simulator here. So here I have chosen the fluxonium qubit, and it has some default parameters shown here. And here you see the potential profile along with the wave functions. So at this point, it doesn't look very interesting. There is some potential. Well, here, there is one state here, one state here. You know, it looks like a slightly different version of a transmon, maybe. Let me see if I can increase the number of levels. I thought if I expand it, I can show you the sort of the parabolic outline of this thing. But let's now change the flux. So you see, as I'm changing the flux, you see that tilt, which I showed you already in the previous graph. And then as I approach half of flux quantum, you get this very nice double well potential with a reasonably tall barrier, but then you also see that there's an overall parabolic thing in the background as well. Now this looks like somebody was asking why classical bits don't have errors, and I was giving this picture that they are really like two highly stable states. Here you have a nice like two stable states here and here, separated by a barrier, which is tall, but not infinitely tall. You know, very nice quantum mechanics 101 kind of problem. And you see that the states here and here will hybridize and give you a symmetric wave function and an antisymmetric wave function as the two lowest energy levels. And what's going to set the splitting between these two? It's entirely the tunnel coupling between these two wells, right? And that can be very small. So in this case, this difference here is typically on the order of few hundred megahertz as opposed to a few thousand megahertz, like gigahertz for the transmon. So the fluxonium is typically a low frequency qubit with the two states having a very weak coupling through this tunnel barrier. And because of that, it has a very weak matrix element to couple to the environment. So it protects this qubit state strongly from the environment by, I think, nearly 2 orders of magnitude smaller than what a transmon couples to. Yes. Yes. Well, I spent 5 minutes in my first lecture saying it's very bad, but I'll tell you why it's not a problem. So before I answer that question, which is an important one, there are higher states here, right? And there's this distinction between states like this. So these are known as fluxon states. Whereas these states in the higher one, which are sort of part of this parabolic potential, they're called plasmon-like states, like the transmon. And one might wonder, in order to carry out measurement, if I just quickly slide back to my slide here, you see that there is a linear cavity here coupled to this entire qubit. So the measurement architecture is actually exactly the same, where you have a linear cavity coupling to your qubit. But we also talked about the fact that the qubit and the cavity are detuned, but not by a lot. Here, the cavity again is typically at 5 or 6 gigahertz, but your qubit is actually at few hundred megahertz. So it seems like it's going to be highly detuned, so very weakly coupled, very small measurement signal. Turns out that you actually have to consider the higher levels, and it's these higher levels which couple to the cavity. And whether the qubit is in the ground state or the excited state, it sort of pushes these higher levels and pushes the cavity, and that gave rise to, again, a dispersive shift of the cavity frequency for 2 different qubit states. So you can actually measure this also quite nicely. So now coming to this question, that here the qubit is at 500 megahertz. So remember, 5 gigahertz was 250 millikelvin. So 500 megahertz is 25 millikelvin in terms of the energy gap. Typical dilution fridge temperatures are 10 millikelvin. Right? So now KT and h bar omega are similar. So you're going to have thermal population. And I made a big deal that it's not great, and it's true, because ideally you would like the system to be prepared in a known state when you just let it relax. Here it's going to relax to a thermal state. So this requires that if you really want to use this as a qubit properly, you need to do some active cooling. You have to figure out a way to reset this population. And then you can do your experiments, because the time scale over which it's going to re-equilibrate with the bath is still set by the relaxation time, right? The coupling to the environment, which I said is very weak. So the relaxation times can still be very large. The only difference is that an excited state or any superposition state will not decay exponentially to the ground state, but it will decay exponentially to some thermal state, which depends on the ratio of KT to h bar. But in terms of the time you have to do your experiments, it's still more or less the same. It's set by the relaxation time, and fluxonium qubits typically have much higher relaxation time because of that extremely small matrix element of coupling to the environment. So how does one do that? There are a few different ways. One is actually using measurement. Remember, I was telling you that you can measure with very, very high fidelity, which means you can project 0 and 1. So if I start the experiment with this measurement, and I'm able to project the system into 0 or 1, and we know, and this is an ideal textbook quantum measurement, if the measurement result says 0, you know that your qubit is also in 0 state. It's no longer in the thermal state. And similarly, if it ends up in 1. So what you can do is you can start your experiment by a measurement, and then there are 2 approaches. If you don't have fancy electronics, you throw away all the data in which you measured the excited state, and you only keep that subset of data, because as I said, most experiments involve ensemble averages. So you can do that. This is called heralding. But, and this is something we use even in the transmon, where you do see a small thermal population, which is actually due to non-equilibrium effects. But in a fluxonium, it might be roughly 50-50, right? Because it's close to the temperature. So you lose roughly half your data. But it's not a big deal. But you can do something more clever if you have the right electronics. Because you know it's in the excited state, you can put a pi pulse and bring it back to the ground state. So that's a conditional feedback operation. And again, these kind of things have been done. There are now lots of ways of doing this in a fast way. Typically, the challenge is that you have to do this very quickly. You can't wait 2 milliseconds to do that, because the system would have re-equilibrated by that time. So you have to do it on the time scale much shorter than the relaxation time, but that is possible. So this is one method which you can do. The other method is that in the fluxonium, it's possible to drive a transition which connects the excited state to one of the cavity states. It's actually a 2-photon transition, but you can actually drive that transition, and then the cavity state is very strongly coupled to the environment, and it will quickly decay back to its ground state. So this is called sideband cooling for those who are familiar with trapped ion systems. This is a very standard piece of physics which is used in many, many systems to cool the things down to the ground state. So, was there a question? So the trick is that you have a high frequency system which is in its quantum ground state because it's cold relative to the temperature. Sorry, its frequency is higher compared to the temperature. And you move the population from your low frequency qubit to the high frequency qubit, and then that decays down, and that's another way you can do it. So both of these techniques are used for working with these kind of experiments. There was a variant of this type of qubit where this splitting was only 14 megahertz, so extremely small. And using various techniques, they were able to cool it down to an effective temperature of something like 190 microkelvin. That's essentially turning the population back into an effective temperature. It's not the physical temperature of the fridge. Not adiabatic demagnetization, it is sometimes called sideband cooling. So in adiabatic demagnetization, you create a population inversion, right? By applying the magnetic field and then suddenly changing it, and that gives rise to the cooling. Here, you're not really doing a population inversion. You are coupling your hot system to a cold system. Essentially, that's one way of thinking about it. So the cold system is a high frequency oscillator. You transfer the entropy out into that. And the measurement also does sort of the same thing. I think you can go to very, very small numbers. The trade-off is that the matrix elements typically become smaller and smaller and smaller. And I will show you one of the set of parameters here. So it actually becomes extremely hard to drive the system as well. And remember that you would like to do these Rabi oscillations and gates as fast as possible. So it doesn't help if you do something and your coherence times becomes 10 times longer, but every gate of yours also becomes 10 times slower. Then you have done nothing. Because, sorry? Oh, yes. So I was coming to that. The solutions are, you can, instead of trying to drive the transition directly, you can do some kind of a Raman process to do the gates, or you can actually drive from the flux side. And one of the papers here from the Schuster group demonstrated very fast gates in this 14 megahertz qubit to do this. So again, fundamentally, these are all not problems, but technologically, in terms of power, what frequencies you can control very well, those things sort of determine the parameter range we operate now. But in principle, if you can get very high relaxation times, then you can work with very low frequency qubits by using these kind of techniques. Yes. Yeah. No. See, there are only 3 circuit elements. There's potential to look. So I can show you, I was not going to discuss flux qubit at all, but I will show you a picture of the flux qubit because it's there in the simulator. It operates in a different regime compared to this. It's actually the dual of the charge qubit with the charge and the flux interchanging positions. So instead of the spectrum varying with the charge, you now have the spectrum varying with the flux. All right. So this was like, I think, the standard qubit. So we can go to, standard fluxonium qubit. Can't see my mouse pointer. So strange. I have to infer where it is. technical support or other Mac users? My mouse pointer has disappeared. How do I get it back? No, this is never, this particular thing has never happened. Okay, it's back. You just hit it a few more times. Right? Yeah, it's back. I mean, it just came back by itself. So, so this experiment in 2021 was nicknamed heavy fluxonium. It's a slightly different parameter regime where you can now see that this well is deeper. So there is actually now a second set of states near the top, and this well is deeper, so the splitting is even smaller. This one was the one which was 14 megahertz or so. And then finally, there is this paper again from about 2020 where it's again a different regime, but now you see that the lowest lying states are not just confined to 2 of the lowest levels, but several lower levels. And this is a very interesting device. I mean, it's not yet really a candidate for a proper qubit yet, but this one is very interesting from its physics point of view. This is called the superconducting quasi-charged qubit, or the blocknium. And what they're trying to say is that now it's actually a band of, you create this band of states at the bottom. And this is claimed to be a missing dual. It should have existed. So just I was saying that the charged qubit and the flux qubit are dual of each other. The blocknium is the dual of the transmon. Okay? So the way to think about it is that the transmon is a nonlinear inductor shunted by a capacitor, but a blocknium is a nonlinear capacitor. So the Josephson junction now behaves like a nonlinear capacitor, which is then shunted with an inductor to create your qubit, sort of like an oscillator. And what it does is that it creates a sort of this new variable called quasi-charge, which is the dual of the phase of the superconducting junction. So remember, you had the sinusoidal or the cosine potential as a function of phase. Now you have this kind of a cosine potential as a function of this quasi-charge. So here in this, this sort of periodic table kind of thing I showed you, the fluxonium is out here where the inductive energy is much larger compared to the charging energy, and the blocknium is way down here. And to do this, you need to make the inductance very, very high, extremely high. And as I was saying, there are these challenges to achieve such a thing. So, you know, if you have never seen these images, you're going to be really amazed. So let me walk you through this. What you're seeing, this here, is that array of Josephson junction, which has literally been uprooted from the substrate, and it's sort of hanging in midair. Right? But it's anchored on this side, and the small Josephson junction is way out here. So this is the small Josephson junction, and these are the different arrays of Josephson junctions, all then connected, and then this goes out to the measurement lines. You can see some of the zoom in of these images. You can see these arrays of Josephson junctions. Basically, you're seeing alternating layers of aluminum on top of each other. Right? And if I remember correctly, they sort of happened accidentally. They were trying to suspend it, but because of the stresses in these films, it naturally curled up and did this, which actually worked out to their advantage because it sort of occupies space in some sense optimally. So, and the way it is fragile, but apparently it survives, and they can do experiments. They've made many, many such devices. And the way it's done is by actually etching the silicon with a process called reactive ion etching. And that process actually does not affect the aluminum at all. So you can just make your device and just etch, and it sort of removes the silicon from the bottom, and they were hoping to suspend it, but instead because of the stresses in the film, it's sort of curled up. And this allowed them to reach these insanely large inductances without suffering from the capacitance problem. And they were able to get into this regime. So it's a weak junction. So weak means small size junction, small Josephson energy. That's this guy here at the top, which is shunted with an extremely high inductance. And they show in their experiment by looking at the spectrum as a function. I'll show you the spectrum just in a second. It agrees with the duality mapping of blocknium into a transmon, which replaces the external flux by the offset charge and introduces a new collective quasi-charge variable instead of the superconducting phase. And they're saying that the exploration of this macroscopic quantum dynamics in this ultra high impedance circuits has applications in quantum computing and metrology. But here is the spectrum. These are the 0, 0, 2, and 0, 3 transitions as a function of external flux, and they look flat. Right? Typically, if you have a superconducting loop and you apply flux into it, you will get a very strong change in the properties. Here it looks flat because it's the analog of doing the same thing for the charge with the transmon qubit. Now, it's not completely flat. You can see there's a zoom in, you can see it's small, but it's much, much smaller than the difference between the. So this first paper sort of demonstrated this idea that you can reach these regimes. It's not really clear this is a qubit to be used for doing quantum computing or things like that. So again, a very extreme parameter range using clever fabrication techniques and the flexibility of these circuits, you can achieve some very interesting physics. Yes?
Yeah, the mechanical motion can be detected. I mean, saying it has consequences. You can do interesting things with it.
I don't remember this. They must have done some studies. So this suspended structure can probably oscillate. And I'm sure you can detect the signature of that in the paper. I don't know, Serge, are you aware of any such things?
I know in transmons that the shocks of the pulse loop have direct influence on
Yeah, that was this recent paper from EPFL, right? Yeah. Sorry, there was a question there.
So what happens to charge noise in this blocknium? Is it?
Charge noise is there, but again, weaker. So because the states here involve many charge states as well. So I think it doesn't affect. So in this first paper, they don't actually explore the coherence properties so much. They only look at the spectrum to see that you have reached this particular regime. That's why I said that it's not necessarily that this is a good qubit for quantum computing. It's a great platform for a very interesting physics regime, which is, I think, impossible to realize to the best of my knowledge in any other known system. No. So, yeah. Yes. Yeah, because this is not charge, this is quasi-charge. It's an effective new variable which they use to express this equation. In this case, is the quasi-charge a periodic variable? I think, yeah, I think it is. Yeah, it is. Yeah. Yeah, I'm not exactly sure. So, I mean, some of these things, I haven't really studied in depth to. So a lot of the stuff today is going to be slightly hand wavy in terms of my explanation there. But yes, I mean, this spectrum here should probably have a periodicity as well. Yeah. Oh yeah. Okay. But no, this is phase. This is phase. This is quasi-charge. So they have plotted it with respect to only from -e to 2e, but I think it will repeat itself over here.
So you said you're going to run from there.
Exactly. Yeah, it should be. Yeah. Okay. So yeah, so I mean, people have studied the effect of mechanics in this particular experiment. I'm not sure whether it caused a problem or not, but this will have some normal mode of oscillation, which can have some effects. So since there was this question about flux qubit, let me just quickly choose flux qubit here. So you can see the flux qubit is typically, there are again various versions. Typically there is 3 junctions, 1 small and 2 large. And the so it very cleverly changes the update to manual when the calculation is heavier. Because here it takes a little bit of time. So as a function of magnetic flux, these are the different levels with the 0 level subtracted. So you have this very strong dependence of the frequency for the flux qubit. Okay, so I'm going to change gears now to talk a little bit about multi-qubit gates. I've been mentioning this, but we never discussed this here. So this is a critical component. You need multi-qubit gates if you want to do any quantum computing. And as I said, it requires qubits to interact with each other. Okay? So I'll start by one of the first experiments which showed such an interaction back in 2007. You have 2 qubits here. These are actually, back in the day, they were charged qubits, but the physics is the same. And this here is a Fabry-Perot cavity on chip. So it's a microwave resonator. This is a section of transmission line. There are these gaps here which act like mirrors. So that confines standing wave in there. You can see sort of this standing wave voltage amplitudes are shown. So you have voltage antinodes here and here, and a voltage node in the middle. The 2 qubits are placed on either side. This was also a demonstration that you can use such a microwave resonator to couple qubits which are physically far away. And there is some size scale here. This is typically about 7 to 10 mm long. So this was an important sort of addition to the toolbox. It was called the bus cavity for coupling qubits. And this is the picture of the actual image here. And you can see this is old school qubits where the Josephson junction is here. And this is the capacitor, very closely packed. This is how we used to make it and used to be very proud of it. Not that interdigitated capacitors were invented by superconducting circuit people. 3 years of Zoom and people still can't keep their microphones on. I mean, neither can I. It always unmutes at the wrong time. No, it was some intense discussion between participants. All right. So yeah, but later on it turned out that packing these electrodes very close to each other actually was a big reason for microwave absorption due to defects at these interfaces. So we then moved on to these very big kind of qubits here. Okay. So the experiment has 2 qubits which are tunable. So both have squid loops, and you can sort of see that this loop is smaller than this one. That is intentional. And then just look at the top plot here. This is showing the spectroscopy, which basically is identifying the 2 qubit lines as a function of magnetic flux. So they undergo these big modulations here. So that is one of the qubits, and that is the other qubit. And the reason for the different areas is that the period of repetition is different, and this was intentional so that at some point they would cross each other. Right? So at this flux bias, both these qubits have the same resonant frequency. So I was mentioning this coupled pendulum kind of model. That's what is going on. You have 2 oscillators, nonlinear, but 2 oscillators, which are now being brought into resonance, or 2 two-level systems which are being brought into resonance at this regime. And here is a zoom in of that. And you can see that they show this avoided crossing kind of behavior, which is what happens when you couple 2 resonant structures. They split into 2 normal modes. Far away from the crossing, the normal modes are the individual modes. Here, they are sort of the symmetric and antisymmetric combinations of the 2 particular states. the symmetric combination sort of disappears here because the drive has an antisymmetric nature and it's not able to excite that particular state. So you don't see a signal here, but you can then fit it. This is their theory calculation. So at this point, the qubits can actually exchange quanta between them. And this becomes the mechanism for creating a 2-qubit gate. Right? It's the simplest, one of the simplest ways of doing it. So after showing this in the spectroscopy that you can couple these qubits like that, they then did a time domain experiment. And first, they of course did Rabi oscillations on both the qubits individually to show that they can measure it. And because both the qubits are part of this cavity, which also plays the role of the measurement cavity. Remember, the measurement is also done by coupling a cavity to the qubit. So here, this cavity is playing a dual role. It's coupling both qubits. It's also providing a way to measure the state of the qubit. But because both qubits are coupled to the same cavity, it's a joint measurement. You cannot individually detect the state of the qubits. And that's what this curve is showing you, that if you have the state down, down, you get a resonator response like that. So you have sort of tuned it up in such a way. And then for each of the other 3 possible states, you get a slightly different response. It's essentially the same physics that for different combinations of the 2-qubit states, your cavity has a different dispersive shift. And you can detect that by different amount of phase shifts for the different basis states. Okay? So you can do joint measurement like this. It has some limitations in general, but this allows you to look at the physics. Okay. Then the experiment they have done, and so pay attention on the top protocol here. The flux tuning in this experiment was done with a coil, sort of really a superconducting coil, which is outside the device, close to it. So you cannot change it very quickly. It's sort of a big inductor. It can only apply slow changes. But if you want to do gates, you have to be able to change the frequency very quickly. This is all solved now. You have ways of getting the flux on chip very close to your device. But back in the day, this particular experiment, they used a different technique to shift the qubits. So what they did is that they first brought the qubits sort of close enough, but not on resonance. Then they actually apply an off-resonant microwave tone, which stark shifts the qubit on which it is being applied, and then brings them into resonance. This is again a very standard technique which is used, not in practical applications, because the stark drive, which is an off-resonant drive, can do other nasty things to your device. But again, to look at this kind of physics, you can do that. So what's happening here is that they apply a pi pulse on one of the qubits, and then they apply this stark shift pulse to bring the other qubit into resonance for a particular period of time, and then they measure. And then this is repeated for the same measurement time over and over again to get the ensemble average, and then as scanned as a function of time. And that's the data you see here, these green and red plots, okay? The fact that they are undergoing sinusoidal oscillations in opposite phases tells you that these 2 states, remember this thing was calibrated here, these 2 states are exchanging population back and forth. It's going from down up to up down and vice versa. And the rate at which it is doing this tells you the coupling strength between these particular qubits. Okay, they have taken this data for the reference to show where the mean levels lie. And the reason they're actually going up like this is an artifact of the experiment because of the stark drive. It's doing an additional off-resonant Rabi driving, which is giving a slow increase in population, which is why you have this weird upward trend. Otherwise, this should have just been a flat signal here. Okay, so this tells you that you can do these kind of time-resolved exchange, and this becomes a basis for doing a quantum gate between these 2. They didn't actually do a gate in this experiment, but following this, there are many, many experiments which use this kind of a technique, but typically they will use a flux pulse, a fast flux pulse to do this tuning. Okay. Yeah.
Hello. Yeah. So you can measure also the relative phase between them, or it's just you can? Yeah. It's just not shown here, but this is
not
something under control.
The question is, can you measure the relative phase between the qubits? Here, it's only measuring populations. If you want to do the phase, you do a full quantum state tomography. So that would require 3 sets of measurements for each of the things, and then you can see that it was not done in this experiment, but this is very, very standard. Towards the end, I have some data for a different experiment which shows that. So this, as I said, in future, in nowadays, usually done with flux pulses. So this is typically the tunable architecture where the qubits are tunable. And sometimes, as I said, even the coupling circuit might be tunable where you can turn it on and off. So in that case, you don't have to keep them off resonant. You can keep them resonant, but the intermediate coupling interaction is again a Josephson junction based circuit, and that can act like a switch and be turned on and off for the right amount of time. In this circuit, the coupling is mediated by this structure, which is always present. So you cannot turn that off. So the way you turn off is by going off resonant and coming back on resonance, okay? So if you don't want to tune this, and there's a practical reason, is that bringing in the ability to change a parameter in your Hamiltonian, here particularly the frequency of your qubit, is a channel for noise to enter, right? And even though engineering has improved significantly and people can do this well, it was sort of considered to be a potential problem limiting coherence. And I think there is still some effect it has in terms of how much coherence you get whenever you have flux lines coming close to your fridge. So there was a need for looking at protocols which don't rely on tuning. So this is called the fixed frequency architecture, and that is predominantly used by the IBM processors. So it's a fixed frequency qubit, meaning that the transmon has only one junction. It cannot be tuned in frequency. And it has some coupling bus. So again, this is the microwave resonator here between the two. And then in this case, the measurement resonator is different, because in a real practical setup, you don't want to mix these two operations because their optimization conditions are different. Because your measurement cavity is typically strongly coupled to the environment, you don't want your the bus cavity, which is mediating the interaction between the qubits, to be strongly coupled to the environment. In fact, you don't want it to be coupled to the environment at all if you could manage. So you have separate measurement cavities and a bus cavity. This is again just something which sets up a standing wave and creates interactions between these two things. So the important condition is that the resonant frequency of the bus is different than the resonant frequency of the cavities, because you actually don't want the qubits to exchange energy with the cavity. These interactions are mediated by what are called virtual photons, where the qubit is actually off resonant and you never really excite the bus cavity, it just mediates the interaction between the two. And these two qubits are also off resonant from each other, but slightly, just enough that you don't get any 2-qubit evolution. But then how do you do a gate? So one particular method, which is quite popular and used in all of the IBM processors, is the cross resonance gate. Okay, so this tells you the picture. You have two level systems. It's a transmon, so there are higher levels, but let's ignore them for now. And they are slightly different frequencies. Typically, this number is somewhere between 10 to 100 megahertz. That's sort of the range in which you work in. And what you do is that you now drive the high frequency qubit, which is called the control qubit, but you drive it with a frequency which is actually resonant with the other qubit, not resonant with itself. So you're driving the control qubit off resonantly, but at a frequency which is resonant with the other qubit. And I'm not going to go into a lot of details here, but essentially what happens is, depending on whether this control qubit is in the ground state or the excited state, when you apply this pulse, it sort of transfers a different version of this pulse to the other qubit. And remember that this frequency is resonant, so it's going to induce a Rabi oscillation in the target qubit, but this changes the amplitude and the phase of this pulse, which leaks onto this, leaks within quotes, and gives rise to an operation here, which is conditional on the state of this particular qubit. Okay. So in reality, what happens is that the target qubit rotates at different rates depending on the state of the control qubit. So if your control qubit is in the ground, the target qubit rotates slowly. If the control qubit is in the excited state, the target qubit rotates faster. And by tuning this up carefully, you can achieve a NOT operation on the target qubit conditional on the state of the control qubit. So this elementary operation is called a ZX, gate, which is of the C0 class. So Zx here basically refers to the fact that the Z state of the first qubit, which is the control, determines the X rotation of the second qubit. And then with additional single qubit pulses, you can create a control knot, which was that example I gave you, I think in the first or the second lecture, as an example of how to do entanglement between two qubits. So this is all microwave gate. There are no flux lines, there's no tuning. So it's very clean in that sense. You don't need a lot of resources, but there are disadvantages. The fact that these two qubits, even though off resonant, are always coupled to each other, they have a cross-Kerr interaction. What that means is that when the state of one of these qubit changes, it affects the frequency of the other qubit slightly. Now that is a problem, because if you now have, say, one qubit coupled to many qubits, then the state configuration of all of the other qubits is going to determine what the exact frequency of the particular qubit you're trying to control, which means you no longer have knowledge of the precise frequency to operate. Now, these shifts are small, typically few to tens of kilohertz, depending on the coupling strength you have done. But that means you can no longer drive it always on resonance. So the way it's done to sort of work around it is that you estimate the band of frequency. So there's some lowest frequency and some highest frequency. And then in between, you will have 2 to the n possibilities, depending on if there are n qubits coupled to it. And you usually drive in the middle. And then essentially what's going to happen is that you're going to accumulate some phase errors because of this fact that you're no longer exactly in the Larmor frequency frame. And over time, it will give rise to unwanted phase accumulations, which will affect your algorithm. So these are called coherent errors, because this is not due to some decoherence process. This is an unwanted unitary operation which is happening in your system. And this is the primary reason, and I had mentioned this, that why IBM chose to keep their connectivity limited. They found that the price they were paying for larger connectivity was much worse in this metric they call quantum volume, which sort of tells you the overall usefulness of quantum circuit. And they are using this. There are lots of experiments which are going on to figure out how to suppress this error. If these were true two-level systems, this problem doesn't exist. They just, this coupling just renormalizes what the states are, and then you don't have to worry about it. The real reason this is a problem is that these are actually the second levels here, and that is the reason why this leads to a problem. So there are experiments where people have changed the coupler in such a way that it suppresses this effect. So you no longer have this conditional frequency shift, but these have not yet translated into real processors. And this is something we are also working on in our lab, trying to figure out how to suppress this for different configurations. Okay, so let's see how I'm doing on time. I have 22 minutes plus 10 minutes for questions. It was 120? I mean, you said it at 125? Okay, so about little under half an hour. Okay, so I'll quickly go through a few of the projects which we are working in our lab, partly because they, again, are an example of the richness of what you can do with these superconducting qubits. I will take questions maybe at the end if there are on that, so that I can finish the other things I wanted to cover. Okay. So this is one of the circuits we developed in our group called the Trimon. It's a 3-qubit circuit, but it's a single device. Okay. So this is what it is. It's 4 junctions in a loop, and each of the junctions is shunted with some capacitance. So the way to think about it is that you have 4 nodes here, and these nodes are all connected with Josephson junctions to nearest neighbor, but there are capacitances between all the nodes as shown here. The device looks like this. It's only trivially more complicated than the Transmon, because the Transmon had a junction or 2 junctions in the middle and 2 pads for the capacitances. This one has a 4-junction ring and has 4 pads in the system. That's it. It's trivially more complicated to make this. And what this achieves is that now, because you have more inductors and capacitors, this circuit has 3 different normal modes in which it can oscillate. So you can no longer think about this 3-qubit circuit as 3 separate things. These are 3 different ways this circuit can oscillate. And the way these oscillations, if you want to visualize them, there is a dipolar mode where this terminal oscillates with respect to this. So you can sort of create an effective inductance between these 2 points. Similarly, there's one which is 90-degree rotated, which is between this point and this point. And then there is a quadrupolar version where these two are at the same potential and oscillate with respect to these two at a different potential. So these are different normal modes of the same circuit. And if you choose the inductors and capacitors carefully, these three normal modes will have 3 different frequencies. So that immediately gives me the ability to address all the modes separately. And I now have access to the full 3-qubit Hilbert space. So it's 3 coupled anharmonic oscillators. It's a coupled 3-qubit system because the coupling comes from the fact that there is nonlinearity. So remember, if this was a linear circuit, by the definition of normal modes is that they are the uncoupled modes of the system. But because there is higher order nonlinearity, that gives rise to the same type of coupling which I was talking about earlier. It's a cross-Kerr coupling, which means exciting one subspace shifts the frequencies of the others. And you have lots of interesting features, like the most natural gate in this system is actually a 3-qubit gate. It's very strange. The simplest gate is a 3-qubit gate. The single qubit gate is actually the more complicated one. And it's fully programmable in the sense that you have full universal control. So this is what the Hilbert space looks like. It's really 8 levels, and they are sort of distributed at different levels. And the arrows tell you the transition frequencies between the different levels. And the important thing is that the correct transitions are allowed. These are all like allowed transitions. And this gives you a full universal control. So by using these 12 different transitions, I have full universal control over this 3-qubit Hilbert space, which basically means I can implement any unitary I want. Just to make one more point is that if I just take these 2 levels here, you can see that here the first qubit is going from 0 to 1. And I also colored the qubits in different things, but it's misleading to think about this transition as representing the first red qubit. It's actually not. It's the transition of the first qubit when the second and the third qubit are in 0. You follow up the ladder to the next red arrow. This is the transition of the first qubit from 0 to 1 when the other 2 qubits are in 1, 0. Similarly with 0, 1 and 1, 1. Yes?
Can you reveal a controlled way of superposition?
Absolutely. So for example, if I apply pi/2 pulse on this transition, that's a superposition of these 2 levels. If I now apply another pulse on this transition, I have now mixed these 3 levels. That is what I mean by universal control. You can create any arbitrary superposition you want in this Hilbert space.
Including a phase.
Including phase. Exactly the same technique.
What is the lifetime of this? Not of relaxation, but of dephasing.
It's similar to what typical transmon qubits have, because these are all, essentially they are transmon-like qubits, the 3 normal weakly nonlinear modes.
How about the GHC state?
Yeah, if I create a superposition between this one and this one, it's a GHD state. I will, no, it's very easy. So you start with a 50-50 superposition of this one and this one by applying a pi/2 pulse on this transition. So pi/2 pulse is just, you do a Rabi oscillation, you go halfway, and then you can apply pi pulses to transfer this population here and then here, or you can go like this. There are many different ways of doing that.
Right, but do you get, high fidelity and how stable is it?
So,
Because you have
yeah. So let me come to the stability question just after I say one more thing, and then I'll talk about that. So if you think about what the operation is happening on one of the transitions, it's really a conditional operation. It's actually a controlled rotation. It's rotating the state of one qubit conditional on the other 2 qubits. So the simplest operation is a 3-qubit operation here. And that's because it's a coupled 3-qubit system. You just cannot imagine them as 3 different qubits. It's a composite system. And the same thing results in complication, because if I want to do a single qubit rotation, which means I want to rotate the state of one qubit independent of the state of the other qubits, what that means is that I have to now drive all the red transitions if I want to do. So if I want to do a pi pulse on qubit 1 only, then I have to do a pi pulse here, 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 and here. So the single qubit rotation now requires 4 pulses as opposed to just 1 pulse. So sort of the complexity has reversed. However, these are all just simple Rabi rotations. And in principle, these operations commute. So you can actually apply all of these frequencies at the same time in a single operation and flip them. Some of you who are familiar with NMR experiments, this is actually how the NMR qubits typically are manipulated. Typically, but the difference is that in NMR, you're always doing an experiment on an ensemble of qubits. You can think of this as doing an experiment on one NMR molecule. I'm comparing it to NMR in the sense of how the qubits are always coupled to each other and you have this Hilbert space. Okay. So the simplest operation is a control-control rotation. If you do a pi pulse, it becomes a control-control knot, which means algorithms which require 3 qubit gates can be implemented a lot efficiently in this kind of subspace. Okay. So we did some one step of a Grover search algorithm some years back. And at that time, we saw that the fidelity of this algorithm in terms of its success probability was one of the best of any 3 qubit Grover implemented till that time. Now, coming to the question of the stability. Now, each of these transition has a very similar character to that of a transmon qubit. So their coherence properties are of the same nature. The problem, of course, is that if you go to this excited state, it has 3 ways it can decay, right? So that makes the lifetime of the excited states smaller compared to what you would have had if you had 3 individual qubits. But nothing really limits in terms of improving the coherence. So at that time, we had decent coherence of about 30-40 microseconds on an average for all of these transitions. And we do see that as states, we go up the ladder and we involve states with higher excitation number, then they become less stable. So overall fidelity does drop. And the other thing you have to worry about, which I have not shown in this picture, is that I have kept only 2 levels in each of the subspaces, each of the oscillators, but there are higher order levels, right? It's a transmon. What that means is that there is a 200 somewhere here, which could be very close in energy to 110 or 011. And if you have those accidental resonances, then you can leak out of the subspace. So you have to fine tune this device carefully in order to get it to work. So you can do that. And this is one of the reasons why we actually made each of the junction, instead of being a single junction, we also made them SQUIDs so that we have some in situ tuning capability to shift these energy levels and then do the operation. Okay. So that's one thing. The other thing I want to tell you about was our work on coming up with a circuit which allows qubits which are non-nearest neighbor to actually talk to each other. So I talked about this connectivity as being an important thing if you want to do more complicated operations. And this is the idea we came up with. What you're seeing here in green is a circular transmission line. So earlier I showed you transmission line which is straight sections. Now this transmission line wraps around itself and creates a transmission line with a periodic boundary condition. You can think of this as a resonator with periodic boundary conditions. And these blue dots are the qubits which are distributed along the circumferences and have some coupling to this transmission line. This, if you analyze the problem, is basically can be thought of as a multi-path coupling element. I'll elaborate on that in a second. You get quasi all-to-all coupling, and the qubits are physically, again, spaced apart to give isolation between the qubits when you're controlling them. And you have reasonably uniform coupling. So this diagram shows what the coupling connectivity is. Each qubit here in this 12 qubit model can interact with 9 other qubits in the circuit without having a direct, like an individual direct connection, because they can all share this common bus which is mediating the coupling. And this is actually how the experimental demonstration looks like. We did it in sort of a 3D architecture where the microwave structure are machined out of aluminum. So this little square box is about this big. And you have this circular transmission line in the middle. And then you have these small sections of transmission lines, which are the readout resonators. These are the measurement cavities. They are designed as a λ/4 measurement resonator. And then in between these two, you see this little chip here, and each chip is 1 qubit. So that's how it is able to couple to the common cavity and also to its measurement cavity. so that you can do it. So in our first experiment, we placed 4 qubits at strategic locations to show all the possible angles that we needed to demonstrate. And the way to think about it is that if you just consider any 2 qubits at a particular location, the excitation from a qubit can travel in 2 directions. It can go clockwise or it can go anti-clockwise. And depending on where the other qubit is, these excitations will meet with different phases. So if they destructively interfere, there is no coupling. And there are 2 such points which are 120 degrees separated where you get this destructive interference at a specific frequency. And then for other points, you either get perfect constructive interference or slightly less constructive interference, and you have 2 different coupling strengths. That's why there are these 2 dark blue and light blue colors. So overall, this gives you almost all-to-all coupling with only 2 different values of coupling strength. In general, if I just distribute them randomly anywhere, you will get all-to-all coupling, but the coupling strengths will be all over the place. So the thing was to analyze it and choose the right frequency of operation. That is basically what is the resonant frequency of this structure and what is the frequency at which the qubits are operating. And one of the nice things here is that it's very modular. And by just moving around the qubit positions, because I can just open this experiment, put the qubits in different positions, I get different connectivity. So for example, if I put the qubits in these kind of positions, I get a lattice which is like a square thing. If I move the positions, I can now activate these 2 couplings as well. There is another configuration which gives you the same kind of a coupling strength. And if you do something different, you can get something like this. So one of the experiments we are trying to do is trying to understand these coherent errors in these different configurations where you have different connectivity. So I don't have to make a new chip. I just have to open the experiment, move the qubits around, and I have a different effective circuit here. Okay. And it's this architecture we are actually using, slightly modified version of that, to build our full 7-qubit quantum computer as well. Again, as I said, this is sort of a choice made by realizing what are the things we can do well, what are the challenges we have with our fabrication. And this is going to look like this. There are actually 2 rings, and this is strange because I told you my single ring can accommodate 12 qubits, but I only have 7 qubits. Why do I need 2 rings? This is because we deliberately wanted the connectivity not to be very high for the same reasons. So by placing the qubits like this, you get a 7-qubit system, which is going to have a connectivity diagram like this. So there's going to be some which are highly connected, some with less connectivity, and some with even less connectivity. And this project is being done in collaboration with a DRDO lab, which is the Defense Research and Development Organization. They started some new labs called the Young Scientists Laboratory in Quantum Technologies, who are working with us on developing the hardware and also developing some custom FPGA electronics. And also a company, Tata Consultancy Services, which is actually an information technology company, they are working on developing the web interface through which people will be able to access this system. So we're hoping that eventually when it's launched, everyone can log in just like for the IBM system and program it via a web interface, and also maybe even using a standard SDKs like ISKIT. And this is the dilution refrigerator where it's going to be coming up. Okay. So I have about 10 minutes. And in the last part, I just wanted to show you a few examples of things which are happening around the world, which are interesting. And then I'll sort of end with some thoughts of my own. Okay. So I'm sure many of you have seen this in terms of applications of quantum computing. There were experiments done by many groups, but IBM sort of solved these small molecules like hydrogen and lithium hydride using a few qubit system, using this technique called variational eigensolver, where you use a combination of quantum calculations and classical calculations on a regular computer. And then a few years later, using this method of error mitigation, where they basically understand how having different amounts of errors makes their results worse, and sort of extrapolate and calculate what it would be if it was error-free. So that's sort of a valid way of doing it, and they have better results in terms of matching of the results from the quantum computer. So this is essentially energy as a function of interatomic distance. And in the first experiments for the simple molecule, the agreement was reasonable. As the molecule became more complicated, the agreements became worse. In this paper, they show much better agreement. There are also experiments for example, making a model of photosynthesis. This was done in the Waldorf group in 2018. And they basically made a model to understand how in photosynthesis this transfer of photonic excitation and into electronic excitation is done very efficiently. And a surprising thing they find out is that the environmental noise, which typically considered as a bad thing, here they actually see that it's the environmental noise which actually helps in some way to improve the efficiency. So it's a model which is sort of scaled down in energy by a factor of 10 to the 5, but these are examples of the kind of things one could imagine doing, right? I'm sure all of you have seen this result from Google from a few years back, where they used a 53 qubit system to do a calculation, which is not really a useful or practical calculation. It's the sampling the output of a pseudo-random quantum circuit, and essentially claim that their quantum computer can do this in about 200 seconds, and their estimate of the best supercomputer will take something like 10,000 years. Of course, this result was highly controversial. People argued about whether it's really 10,000 and so on and so forth. But this was sort of the first experiment where they claimed to show where a quantum processor actually does better than the best classical computer you have. And a year or so later, a similar experiment was repeated in a group in China with 56 qubits that immediately increases the size of the Hilbert space by a few orders of magnitude. And there they had a more modest comparison. They're saying that the quantum computer does something in 1.2 hours versus 8 years for a supercomputer. That was also on a similar architecture with qubits with tunable couplers and tunable qubits as well. These results are still somewhat controversial, and there have been many criticisms of this estimate. Some people say that very recently there was a paper which said that you're assuming for your estimate, you're sort of assuming that you had a perfect quantum computer, but your quantum computer is very noisy. So if you take that into account, then maybe you don't need that long to reproduce the result. Very recently, earlier this year, and we were discussing this in our first lecture, that can NISQ computers really be useful? So IBM published a paper with the title which says that evidence of utility of quantum computing before fault tolerance, it's basically before the era of error correction and fault tolerant computing. And they did it on this 127 qubit system with very good coherence. This is their IBM Eagle processor with 127 fixed frequency transmon with this heavy hex connectivity, which is this thing over here, T1 and T2 times of around 300 and 150 microseconds or so, just really state of the art. And to have that over the entire chip is quite impressive. For example, in our labs, we typically get 50 to 60 microsecond at the best, but of course, many other groups have measured qubits in this range. And this is sort of quote from the paper. We report experiments on noisy 127 qubit processor and demonstrate the measurement of accurate expectation values for circuit volumes at scale beyond brute force classical computation. So again, this is not really a useful calculation. This is again sort of implementing some circuit and trying to predict the outputs. And they're saying that now with this much superior quality of qubits and better calibration and understanding of the noise and mitigating it in the same way, they argue that this is evidence for utility of a quantum computing in a pre-fault tolerant era. This is very recent from June of 2023. Last two examples. This is sort of not directly connected to superconducting circuit itself, but it is in the broad field. This is this error correction breakthrough, which was made again earlier this year. So let me just tell you the picture. What you're seeing here in gray is a cavity. It's a microwave cavity. It's actually a coaxial stub cavity. You can see this central line here. And they basically figured out how to make this very, very high quality factor, which means extremely low loss. So the photons live for a very long time in these cavities. And it is coupled here from the side port to a transmon qubit. So this thing here is a transmon qubit. You can see the nonlinear potential. And then here is a readout resonator to read the transmon qubit. So here the quantum states which you're trying to use for quantum computing are not stored in the transmon. They're actually stored in the cavity. The transmon is there as a nonlinear element enabling you to do operations. If you only work with linear systems, you can only create coherent states, which is not very useful. So that's why you need the transmon qubits. It's sort of an indirect thing. The quantum states are here. This is a particular implementation called a GKP code, which I will not go into. In fact, I don't even understand it very well. The bottom line of this result is, remember that error correction can be called successful when your combined qubit, which takes many different elements, is better than the best element you have in your system. Right? Now, typically all the elements are the same. In this experiment, all the elements are not the same, because what are the elements? You have a transmon qubit, and that is the coherence of the transmon qubit around 200 to 300 microseconds. So that's the coherence of the transmon qubit. This here is the qubit created by using the ground state and the first Fox state of the harmonic oscillator, which is highly long-lived. And you can again do that experiment by actually first putting the excitation on the transmon and then swapping it to the cavity, because you cannot directly create a Fox state by driving a harmonic oscillator. And that is roughly 2 to 3 times higher than the transmon qubit. And then when they implement their error correction code, they see that the combined, what they call as the GKP qubit, has about 2.5 times the coherence times of the best qubit, the best element, which is this one. And the reason this is limited is again because of the coherence of the transmon. So even though it is only involved in the operations, the fact that it is incoherent, not as good as the others, sort of is one of the limiting factors. Though this experiment was possible because of this new tantalum-based qubit technology, which allowed them to push their qubits from usually around 100 microseconds to close to 300 microseconds. So this was a big result. And in parallel, there was a group in China which also did a similar experiment, but their improvement was not a factor of 2.5, it was just about 1. But they also showed this similar kind of experiment. So it's a big deal that for the first time, you've actually shown an error-corrected qubit which lives longer than your elements, but it's still a far cry from being able to use this in a practical quantum processor. Okay. And the last two ones here is this experiment with an array of Josephson junctions from the group of Vladimir Manocharian, where they're looking at the quantum electrodynamics of a superconductor insulator phase transition. Somebody was asking about this, I think, in one of the lectures. So this is an array of Josephson junction, again, using all these crazy techniques I mentioned in some slides ago. So they say that the chain of Josephson junction is one of the simplest many-body models undergoing a superconductor insulator phase transition. So here they say that apart from the zero resistance mode, the superconducting state has this sound-like mode due to the collective oscillations of the phase of the complex valued autoparameter. And this, I think, had not been explored in these kind of regimes. And here they demonstrate that this actually is there, and it can carry high frequency gigahertz currents. And this is sort of the physics of the electrodynamics of a Bose gas. I'm really just dumping information for you to know that these kind of things are possible. I know very little about this experiment, but you can see it's just an array of Josephson junctions. And they're saying that the effective fine structure constant of such a one-dimensional electromagnetic vacuum exceeds unity. And that really puts you into a different regime of physics and can have transformative applications. And this is the selling statement here, but this is a very interesting regime, which is again was not possible before. The last example, and this was sort of coincidentally I included because yesterday someone wanted to understand this experiment and I was discussing, and this is again fundamental physics about quantum measurement. And here they're actually talking about catching a quantum jump, which is a transition of a qubit from one state to another. And while it's transitioning, you sort of stop it and you reverse it. So the catching itself is somewhat surprising, but once you can catch, I think the reversing is not so surprising if you once understand what's happening. So let me just take a minute to explain the setup. It's a 3-level system. It's actually created by coupling 2 qubits to each other in a strongly coupled manner, very similar to the trimon where it had 3 qubits and you had 8 levels. There is actually a 4th level here, which is not used in the experiment. And it's engineered in such a way that this transition is strongly coupled to the environment, and it's called the bright mode. And this transition is weakly coupled to the environment. It's called the dark mode. This terminology is coming again from atomic physics and ion trap kind of systems. And that whole thing is coupled to a linear microwave cavity through which you can do the measurement. And the coupling is also arranged in such a way that the microwave cavity can distinguish which means it has two different phase shifts for the ground state and the bright state, but it has a very small phase shift for the ground and the dark state. So essentially, it cannot measure this difference. It can only measure this difference, which means it's implementing a measurement which says, are you in B or are you not in B? Okay, that's the kind of quantum measurement they're doing. And the way they do this experiment is that they drive this transition continuously while measuring with a very strong drive, and they drive this transition very weakly so that this transition happens over a much slower time scale than these transitions. Now, as these transitions are happening, that is causing the cavity to respond. And these are all these blue curves here. And of course, you are Rabi driving and measuring. So it's kind of a Zeno kind of problem. So the qubit is trying to change state, but not in a coherent way. And then the measurement projects it. So you sort of get this telegraph-like behavior between these two levels. And that is what is happening here. And these arrows mark the location each time the system leaves the bright state. And because they don't know when it leaves the bright state, whether it is in the dark or the ground, because the cavity cannot distinguish that. But then what they see is that there is a particular signature which shows up where suddenly these transitions stop happening. And that tells them that now the system is about to go to the dark state. And then the moment it reaches the dark state here, this drive is no longer effective. So you don't have that very strong signal coming out of there. And so the red points here mark the dark state. And it is this transition which they're calling as the quantum jump. It's the quantum jump between the ground state and the dark state, which happens less frequently. So all of these parameters have been arranged to get these two different time scales and to implement that measurement operator, which allows to do that. And what they claim here is that by looking at these events, they actually get this pre-warning that suddenly it goes quiet. They know that this transition from ground to dark is about to happen. And because they can herald that time, they basically repeat this experiment for different waiting times and essentially do a quantum state tomography on this subspace. And what they find, and this is the interesting part, is that this process of jumping from the ground to the excited state of the dark subspace is fully coherent. It's like a rotation on the Bloch sphere. And that's what this tomographic data shows you, that the Z goes from -1 to +1, and the X rotates, because the X changes as you rotate, and the Y remains the same. So what happens in X and Y is sort of all set by the phase of this drive here. And they're able to show that this jump is a coherent process. You can herald it. And because you know the time scale at which it's going, you know exactly when it's going to be halfway, you can now send a pulse to undo that effect. So that is the catching and reversing of the quantum jump. So, very fundamental quantum physics kind of experiment. Again, everything agrees perfectly with theory. Nothing is new in the sense that no quantum mechanics has been violated. I keep liking to say that quantum mechanics is surprising only when you don't believe it. So a lot of these experiments, they go into these regimes which are very counterintuitive to understand, but everything agrees perfectly with the way, if you analyze your problem correctly, just like various experiments like quantum erasure and other things, right? So that was this experiment. So this is the last thing I want to show you. I'll conclude by saying that this superconducting platform is a highly coherent and flexible platform for doing experiments in the quantum regime. You just have these 3 building blocks. Really, it's up to your creativity to build what you would like to bet. And the ability to realize different Hamiltonians and in different unexplored regimes offers really tremendous opportunities for new and interesting physics. And there are regimes of quantum optics, which I've not had time to discuss, which are impossible in an optical system, but you can do that with microwave light. It's also the most advanced and most promising platform for building a practical quantum computer. The basic building block is reasonably understood. We know how to make qubits. They're getting better and better, but it's not perfect yet. Maybe we still have to invent the best qubit. And to really make them useful, you need to scale, which requires a lot of resources, good fabrication, good electronics, good engineering, a lot of time. And the few things you have to solve is that you have to make these building blocks more robust to errors and increase the coherence. You have to get the electronics scalable. I gave you this example of how many components it takes to control 1 qubit. You can't just multiply that by 1,000 or 1,000,000 to make practical systems. one does have to work on the interconnectivity architecture to get more dense connectivity without having errors, and quantum error correction is going to be a very important milestone to turn this into a practical, useful system. So I'll end there and I'll take questions. Thank you.
Okay, questions? Oh, use the mic, please. Is it on?
Thanks for this very nice overview. So you also showed us a lot of different qubit types, but it seems all the big companies focus on transmons entirely. So what do you think are the chances that these new innovations in sort of qubit technology will influence the bigger companies?
Right. So as of now, the transmon gives you the most bang for your buck. It's extremely simple structure in terms of making it compared to some of the more complicated ones. There was also this incorrect notion that if you have many junctions in your circuit, they may not be coherent, which has been proven completely to be false. The fluxonium is actually emerging as a real candidate, an alternative with much higher coherence times and much higher unharmonicity, which simplifies some of the problems of having these higher levels. You don't have to worry about accidental resonances. So people have demonstrated 2-qubit gates with fluxonium, but it does have this extra requirement of having a flux control. So with these big companies, they cannot change gears very quickly, right? So it's going to take a lot of convincing, and they're going to push. And it's quite amazing if you think about the fact that only IBM seems to be able to create aluminum qubits on silicon with 300 microsecond T1. And recently at a conference, they showed data of one or two experiments where the coherence time has exceeded 1 millisecond. They're not yet made to their processors yet, but most other groups will be around 100, 150 microsecond. We don't know what they're doing, right? There are these alternate superconductors like tantalum, where experiments have been done and people have made a few hundred, even 500 microseconds, I think a group in China, and very recently in niobium. Again, Josephson junction is still aluminum. So for the companies, I think it'll require someone to convince. It's possible that Google and IBM are working on fluxonium qubits on the side. We just don't hear about it just yet. So I think it will eventually can happen if the transmon hits some kind of a limit. But as of now, doesn't seem to be. But the fact that it's weakly harmonic can be an issue. There have been studies which show that if you connect too many of these oscillators together, and here the connectivity is a problem, then you can get some kind of chaotic regime where things will become very unpredictable. But I think it's not such a serious worry, but other groups are trying, and I think fluxonium is very well placed. Things like the blocknium and the other things, they are more from, on point of view of physics interesting regimes of quantum mechanics. They're not yet really, they don't have qubit, like good qubit-like properties in terms of being able to manipulate them easily, make a large number of them reliably, and so on and so forth. Yeah. Serge, do you want to add something to it?
There is a new startup company called Atlantic Quantum who are using fluxonium, and I think also Alibaba are working on fluxonium.
That's
you
right.
have a few companies working on these bosonic qubits with harmonic oscillators. So there is some diversity.
Yeah. Yeah. Yes, I mean, these other things are not yet that much in limelight as IBM and Google, but it'll happen. Yeah, the bosonic qubit processes will hear something sooner than later. And Alibaba has shown gates between fluxonium qubits, but what I mean is that we haven't seen like a 5-qubit or a 10-qubit processor just yet. I mean, it's at this stage, it's really you just have to do it, and it will work. Whether it introduce some new complications, one has to say. Okay.
Other questions?
The back there. Turn it on. Wait 3 seconds.
Yeah.
Yes, please.
So I want to ask about these higher modes, how like there is some upper bound for the these control fields so that you don't excite these qubits to the higher modes. And apart from that, one more question about scalability.
Yeah.
And how.
So when you have this transmon qubit, and you are trying to manipulate these two levels as fast as possible, right? So what is fast here means it's a very short pulse. Now, the Rabi principle tells you that you can make the amplitude arbitrarily large and your time will keep shrinking. But as you make your pulse shorter and shorter, this pulse in frequency space is going to represent a very high bandwidth around the mean frequency, right? Short pulse means high bandwidth. Delta function is infinitely long pulse. So when that spread starts to approach omega 1, 2, then you start transferring some energy from 1 to 2. This is called the leakage out of the subspace. Okay, so this is sort of the fundamental reason why you have some limitations on doing this operation in the fastest possible way. However, this is a very simplistic picture. There are techniques where you can apply a more complicated pulse which sort of burns a hole in the spectrum exactly at these frequencies. Then you can go faster. So there are various techniques like drag and other things people have used. So by using that, you can push it a little bit faster, but at some point you will get limited in the transmon. Now, currently the gate operation time is still quite fast, that it's not a serious concern because the 2-qubit gates are significantly slower. So until that becomes much faster, you don't necessarily have to worry about improving, but you see new papers on doing various kind of optimal control based techniques to improve these pulses. So that's the primary reason. If this level was far away, you can do much faster gates as well. So you said, what about scalability?
Yes.
What's the question?
Scalability, like for now, what is the constraint and how it can be this system with the transmons? How much it can be scaled up, like in future, in near future?
Well, so if you have followed the progression of the IBM processors, in fact, this picture here, where's my this picture here, which is their latest, I forget, it's the 401 qubit. These are actually different layers of chips. In one layer, there is the interconnect circuitry. In another layer, there are the qubits. In another layer, there is the readout circuitry. And they had to do this because as you pack more and more qubits in a single planar architecture, you have physical problems of getting the wires into the right place. And how do you access the qubit right in the middle? So unless you start using the third dimension in some way, you have to, things get more complicated. As you add layers, every fabrication step and processing can potentially introduce some kind of complication or contamination. So you have to do that carefully. So at this time, it's really a question of how much time and money you're willing to put in to solve those problems to get to larger and larger. I mean, IBM has a roadmap of getting to 1,000 qubits or so by next year. The other question, which I think is more interesting, is that what do you think you're going to do with that 1,000 or a 2,000 qubit? I think that also has to be answered in parallel, because if you just keep making longer and longer set of qubits, which are not that well connected, it also limits the kind of things you can do. You have to keep increasing your coherence times as well as your circuit's qubit size is becoming bigger, because then having 1,000 qubits with very poor coherence is as useless as having a very small number of qubits. So these things take time. And people are working on these different aspects, but nothing fundamentally limits you from making bigger and bigger chips. At some point, you start worrying about how many measurement lines are coming down my refrigerator, how many components can I pack, because this chip itself might be quite small, but all the supporting electronics is very bulky because they are typically at microwave frequencies. The wavelength sort of determines their characteristic size typically, because they're all based on some kind of transmission lines. And that becomes a problem. And IBM, for example, is working with a fridge manufacturer to build gigantic dilution fridges. They really look like you can actually walk into them. They have these, I forget the name of that thing. And these are all steps to make bigger dilution refrigerators to pack a lot of these things. There's of course criticism on the other side that they say this is crazy. You can't pack millions of qubits in some room-sized dilution refrigerator. But it really depends. People who work in that field, they understand the engineering challenges and they know that this is worth following. Others will say, okay, no, our technique is better. So, yes. Is bringing the qubits into resonance same as entangling them? No, you have to bring them into resonance for the right amount of time and then take it back. Otherwise, they will get evolving from an unentangled state into an entangled state and back and so forth. And then when they are actually on resonance, then it's sort of really a hybridized system. So you really want that exchange to happen, and then you want to decouple them so that they are now entangled and no longer coupled to each other.
How these light harvesting models are related to these experiments?
How it is related?
You talked about the light harvesting models. And
so that was just an example of doing a certain kind of a calculation on a superconducting circuit, which mimics what happens, or at least they try to mimic what happens in photosynthesis. So it was more about if I remember correctly, it's about how the excitations are transferred very quickly and efficiently from optical to some electrical domain. They did some analog modeling. So these kind of experiments are often called as quantum simulations. You're simulating a real physical system with your building blocks, which mimic, but with the right quantum mechanics in them. And that is sort of an important class of problems.
So one more question is, when you were talking about the avoided crossing, you said about the mechanism of what happens to the dark state and the bright state. So can you repeat that part again? What exactly happens there?
Basically, I have shown data where the spectroscopic signal disappears when they are exactly on resonance, which corresponds to the symmetric state, which is the 0, 1 plus 1, 0, or up, down plus 1, down, up state. And the reason for that is that the microwave drive, which is doing the spectroscopy, has an antisymmetric nature, and it cannot excite that state. That's the reason there's a little bit of hole. But maybe I can explain to you offline in more detail what's going on. They're just explaining why there is a gap in the spectrum.
Yeah. One question here.
Sorry, was there something else?
It's me. Somewhat a more fundamental question, which I used to know the answer to, but I forgot. So the very last example that you gave about catching a transition on the flight, it is known that when you have a two-level system subject to a drive and dissipation, it is described by Lindbladian. But if you don't have jumps under the condition of no jumps, it is described by a non-Hermitian Hamiltonian, actually anti-Hermitian Hamiltonian.
Okay.
But now you are saying that this transition, which involves no jumps, is actually described by some effective Hamiltonian, effective rotation in a Bloch sphere. So how the two statements are compatible?
Okay, so I'm not exactly sure to which non-Hermitian description or anti-Hermitian description you're referring to, but I remember discussing this and asking about the fact that, so this apparently cannot be done for the jump in the opposite direction. And that's got to do with the fact that the measurement operator is really asking this question, are you in the bright state or are you not in the bright state? So let me elaborate. Remember what's happening here. You are actually studying the quantum jump of these two levels. That's the one they're actually trying to catch. But it is not this which is measured by this cavity directly. It's an indirect measurement where the measurement of this subspace gives you information about what's going on in this subspace. So it's deliberately engineered. Otherwise, because you can observe these jumps on just a two-level system directly coupled to it, right? But this kind of signature, I think, is not there. So I don't understand that part in such great detail, that why the reverse one doesn't work. But I don't think there is anything non-Hermitian or anti-Hermitian going on here. I think this is still standard, but maybe we can look at the paper and see if there is something more. Yeah, sorry, I don't know more on that. Right at the back, yeah.
So as you just mentioned, this superconducting transform qubit is a well-accepted architecture, but there are very few metrics which have been developed like Q-score or quantum volume. So they basically tells us about the capacity of how a quantum processor can perform. But they don't basically give some idea that if I want to solve a particular problem with like n number of qubits, I mean that n can be small or high. So like what properties to look upon before mapping my problem to the hardware which is accessible over cloud or something, because the hardwares which are available over cloud, they don't allow us to tune all the controls which are in the low level. So can you just suggest some ways that if trying to solve a problem, let's consider any algorithm which can have like small or higher number of qubit requirements, like what factors to look upon before solving my problem with a specific hardware?
That's a very tough and general question. I mean, so I actually don't work a lot on thinking about how to run algorithms on different kinds of computers. But something you said earlier, these metrics have nothing to do with the type of qubit, right? Quantum volume is not transmon specific. You could have a processor with anything and you can, right? And that is just some metric they invented because no such metrics really existed to talk about comparing, say, two different types of processors. And I think the notion there was that this metric tells you something. It sort of tells you, okay, how long a useful circuit you can kind of implement. But the most generic problem of just taking any problem of your interest and figuring out what metrics to look for, I think there's no simple answer to that. I mean, you will have to do the hard work in understanding what the processor allows, how that limits your problem. Or the other way, you can say that, well, I feel that it would have been better if the connectivity was slightly more denser or if the measurement fidelities were better, so on and so forth. So, I mean, there's no simple answer for this. Sorry, did you have a comment on this? Okay. Yeah. So the other point you said is that, yes, the kind of access you get depends on how much money or how much free you are using. So there are, from what I understand, there are various levels of access. I think some universities in India now have a more enhanced access, which gives you more time. I know that IBM has also introduced some pulse level control, where instead of just saying apply these sequence of gates, you can actually do experiments where you say send this type of a pulse. So that is actually more to understand, or if you want to optimize the gates yourself, those kinds of things are also possible. But I think for a more dedicated access, you'd probably have to tie up with them and have a joint project. I mean, that's what I'm assuming. We are hoping that in this simple 7-qubit system, eventually when we launch it, apart from the simple access, we will work with various researchers who can access it at a lower level, even come to our institute and use it together with us to do more interesting experiments as well, as a sort of a more general purpose platform. But I think such things are available for others, but I'm sure it costs a lot of money and we'll have to shake the right people's hands as well. So.
So nice talk, by the way. So I think this is more of a comment to one of the questions that was asked about this experiment by Devoria. So I think the premise of this experiment is like the theoretical premise is quantum trajectory theory. And I think if you postulate a particular trajectory, you will have the dynamics dictated by a non-Hermitian Hamiltonian, but that's for the unnormalized state. So I think that's what the connection is, in the sense, because the transition is coherent and deterministic. It's like the state is governed by a non-Hermitian Hamiltonian if you're not considering the normalization, if it's unnormalized. So I think, basically the question that was asked yesterday was Abhishek Dhar, he's my advisor. So we are interested in looking at this paper further.
I was talking to Abhishek Dhar yesterday, which is why I decided to.
And the question I have is basically, are people looking at this particular, like these foundational ideas for more general systems, like say a qubit, multiple levels and multiple qubits, for example. So because those,
I know people are working with qubits as well, but specifically for this kind of experiments, I'm not sure. I mean, one of the problems, this field has exploded so much that it's become impossible to really keep a tab. I mean,
absolutely.
So I'm not aware, but I know people are working with higher number of levels in the transmon and doing interesting things. There are even protocols for error correction, which are actually simpler in a 3-level subspace. in terms of what you can do with just a few objects, a few transmons. For
Right, that's what I was thinking, because apart from being a foundational work, it also seems to have applications to detecting error syndromes and quantum error correction. So I think it's an interesting work in that way.
Yeah, I mean, if you have ideas, we can talk about how to turn them into experiments.
Yeah, so it's more of a curiosity about a technical thing. So you write these circuit diagrams with the Josephson junction written as a lumped circuit element.
Yes.
So, but we know that it's a nonlinear circuit element. So in the analysis and design of all these circuits, which are important for gates, so does the fact that the Josephson junction being a nonlinear, how much does it affect? So usually you treat this, you have methods for analysis and design using linear circuit elements, right?
So first, you invoke the idea of Josephson junction as a lumped element, right? The lumped and nonlinearity have nothing to do with each other. They can be anything and nonlinear or not nonlinear. Yeah. In fact, the Josephson junction is probably the most lumped of all the microwave circuits here. What does lumped mean? It means that the size of your object is much, much smaller than the wavelength at which you're operating. The Josephson junction is tiny. Your capacitors are much bigger, so they are not truly a lumped element. You know, there'll be some gradients across their structure, but usually we don't worry about that. They just renormalize the properties.
Sure, but the nonlinearity is, yeah.
I mean, the nonlinearity is what is giving you this energy level structure. So it's critical to the analysis, but beyond some very basic things like, okay, just giving me some Duffing-like spectrum, it depends on the particular experiment one is doing. So I didn't have time to discuss, but I had sort of briefly mentioned is that when you try to do the measurement with very large number of photons, then you see that even though the simple Hamiltonian doesn't allow such processes, the actual Hamiltonian can, you see excitations from the 0-1 subspace to higher levels, in fact, many higher levels as well. So then to understand that, you need to have the full nonlinear description to calculate all the higher energy states. The bosonic code, the cavity cat states where the transmon qubit is used as a nonlinear element. There are other versions of that where instead of a qubit, you have some nonlinear circuit which introduces a very special type of nonlinearity, and that can induce a special type of dissipation which stabilizes certain states. So there you have to do a full nonlinear model. So the nonlinearity here is not really like a bug which you have to worry about. It is an essential feature of all of these systems.
But the standard methods of the analysis and design, they don't apply.
So I guess by standard method, so for example, for weakly anharmonic systems, like the transmon or even this trimon thing I showed you, the 3-qubit system, you can, so the way we analyze this is that you first linearize the model, calculate the normal modes, and then put in perturbatively the nonlinearity. That works well for such systems. But for things like fluxonium and charged qubits, you can't do that. You have to write down the full proper Hamiltonian. Often you will see that transmon Hamiltonians are written in the harmonic oscillator picture, just as A dagger A plus A dagger A square with some parameter. And that's good enough for most of the cases, but for other kinds of qubits, it doesn't work out. So you have to do the full modeling. Right. Thank you.